Swayam Prabha. Digital India. Educated India.
Change in dipole moment, yes, but do we all know about transition moment integral? Transition moment integral is just this. Are we familiar with this notation? Huh? So what does this mean? So what is Kate? If I now and suppose I write only this, what does it mean? Psi f star integral, is there an integral? When you write Bra and Kate together, then only the integral comes. How will you write integral without dx? So this just means the complex conjugate. When you write them together, of course this line is only to ensure that it is a nice symmetric looking thing. That second line is not even required, one line would have been enough. Okay, this is just to make it symmetric. Nature loves symmetry, we are natural creatures, we also love symmetry. Okay, so this is called transition moment integral, and those who have not studied this spectroscopy course, when you study it you will learn that for any transition to take place, this transition moment integral must be non-zero. If a transition is to take place, suppose you have two levels, okay, this is level I, this is level F, psi I and psi F. Now some light comes and causes a transition from psi I to psi F. Just because you have the levels, it is not necessary that the transitions will take place. Okay. So what you are going to do, if you have not done it already in some course, is called a semi-empirical treatment of interaction of radiation with matter. There you are going to use time dependent perturbation theory, you are going to model light as a wave and you are going to model the molecule as a two level system to start with, and then using time dependent perturbation theory you are going to see that this is the all important quantity, right. You learn that this transition or this transition for that matter induced by light can only take place when integral psi f star mu psi I d tau is non-zero. Okay. If you have not studied it, let us take this axiomatically until you studied it in some other course. Most of the people have studied this somewhere, right? Whoever has MSc has studied it, I hope. If you have not studied it, just believe me for now that this is the essential condition for IR activity. How does a microwave oven work? It heats up the water molecule, right? Any food that you eat, unless you are a stone eater or something, any food that you eat contains a lot of water, alright. So what happens is this entire food item behaves like an oven, okay. All the water molecules inside start rotating, but they cannot rotate forever, so they have to give up the energy, excess energy that they have acquired, and there is some mechanism called dielectric friction by which this rotational energy gets converted to heat energy. That is why food heats up very fast, okay. It is the water inside. The problem is, what is the formula of oil, chemical formula? I also do not know what it is, all I know is that it is non-polar, right. I do not know what is the formula of the oil that we eat, it must be a mixture of so many things. but then it is non-polar, that is for sure. Oil is not polar. So, if you keep a bowl of oil inside the microwave oven even for 15 years and keep the oven on, it is not going to heat up. Okay, why? Because these oil molecules are not microwave active. Okay, so that is a condition for microwave activity. For vibrational transitions, what will happen? If you consider this kind of a transition, if it is a dipolar molecule, then dipole moment is going to change, right. So, you should consider the dipole moment to be mu 0, dipole moment at mean position, plus x into del mu del x. Okay. So, that goes into the transition moment integral. Right now, for the simplicity, we will just write mu and be happy about it. Now, so for IR activity, what is the essential condition? Let us see. What is psi I? Psi I will be psi V equal to 0, right, right. And what I will do is I will use a subscript k also, because any polyatomic molecule is going to have 3n minus 6 number of normal modes of vibration. Let us say this is a kth normal mode, the ground state has to be the V equal to 0 state. Agreed? I think we all have studied quantum harmonic oscillator. We know that V equal to 0 is the only vibrational level that is populated at room temperature. Okay. So, that has to be the initial state. And most generally, this also, if you have not studied molecular spectroscopy, you will learn it that course, psi f is generally psi k V equal to 1. This 0 to 1 transition is called a fundamental transition. Alright, and for a simple harmonic oscillator, the selection rule that is there is delta V equal to plus minus 1. How do you derive the selection rule? That also you can derive from here actually, but that is the story for another course. We will not go into that now. It is not very difficult to derive it. Okay. So, what we want to do is we want to replace psi k V equal to 0 here, we want to replace psi k V equal to 1 here, and mu is what? What is mu? Mu is, you can write mu x plus mu y plus mu z, vector sum, right. Mu can have 3 components x, y and z. So, essentially what we need to see is whether this psi f x, y, z, psi I is this non-zero or not, and that is something that we can do. So, basically I have written 3 integrals here, right, psi f x psi I, psi f y psi I, psi f z psi I, and we are going to see by symmetry when these are going to be this integral is going to be non-zero and when it is going to be 0. Alright, what is the condition for an integral to be non-zero? Now think in terms of symmetry. What I am saying is, instead of writing mu, I can write x or y or z, mu x or mu y or mu z, and these are just aligned towards x, y and z, right. So, whatever symmetry property x and y and z will have, mu x, mu y, mu z will have the same property. So, I have to consider 3 integrals. One is psi f x psi I, second is difficult, psi x psi f y psi I, third is psi f z psi I. Not only do I have to keep my pen that way, his head also has to be in a particular way, otherwise there is eclipsing. So, any of these 3 integrals, if you find that it is non-zero, then the transition will be allowed, alright. Okay. Now, you tell me, if this is an integral, right, what is the condition that an integrand has to satisfy so that the integral is non-zero from the point of view of symmetry. So, if I put it in a very general term, can I say that this integrand has to remain invariant under any symmetry operation for the integral to be non-zero? Yeah, parity will give you the same thing, provided you are working only with your one dimensional representations, it becomes plus or minus. See, if the integrand changes, okay, suppose there is a transition in a molecule going on, you apply a symmetry operation, you get back a molecule in an equivalent configuration, right, indistinguishable configuration. Is there any reason why a transition that was taking place earlier should not take place now? Is there any reason? If I perform a symmetry operation, now if I perform a distortion which is not a symmetry operation, then something that was not taking place earlier might take place now. But if I perform a symmetry operation, then this integral should remain non-zero, right. So, the integrand should remain unchanged upon symmetry operation, all right. So, I should work only with the integrand to start with. Psi f, then x or y or z, I am writing this in short, do not get confused, x or y or z psi I. What I am saying is that this must contain a part that is totally symmetric. Totally symmetric means does not change when any symmetry operation is applied. Okay? So, this thing is called a triple product. When you multiply 3 functions together, it is called a triple product. When you multiply 2 functions together, some phi 1, phi 2, this is called a direct product. A triple product is just an extended direct product, nothing to be scared of, right. So, first you take this direct product, you get some function, then you take a direct product of that function and this one, that is all. So, the question that we want to ask is, when does this triple product contain a totally symmetric representation? When does a triple product contain at least a part that is totally symmetric? Forget about odd for now, we have a better answer now. So, what we really want to do then is that we want to know when does a direct product contain the totally symmetric representation. Okay. See, this belongs to some symmetry species gamma 1, this belongs to some other symmetry species say gamma 2. If you take a direct product, this is written as direct product, okay, convolution sign. If you take a direct product, what do you get? Should you not get a reducible representation? Gamma 1 is an irreducible representation, gamma 2 is another irreducible representation. When you multiply them by each other, you should get a reducible representation unless gamma 1 and gamma 2 are one dimensional. If gamma 1 and gamma 2 are one dimensional, then what happens? All characters are either plus 1 or minus 1. When I say direct product, what do I mean? This is what I mean. Let us say C to V. What are the symmetry species? E, C2, sigma V dash. And let me take any two representations 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. What is the name of the first one? 1, 1, minus 1, minus 1? A2. And what is the second one? B1. Very good. I want to know what is A2 cross B1. 0. Actually, it is B2. Let us see. Just multiply these characters together. 1 into 1 is 1. 1 into minus 1 is minus 1. Minus 1 into 1 is minus 1. Minus 1 into minus 1 is plus 1. What is it now? And once you have done a few of these, it becomes very simple. It is like multiplying by 1 and all. 1 multiplied by any number is that number, right. Similarly, A multiplied by B is always B. B multiplied by B is always A. Why? Because if both were B's, then what would happen? This character is minus 1. So, minus 1 into minus 1 is plus 1. So, you multiply two B representations, you get an A representation. Similarly, 1 multiplied by 2 subscript is always 2 and 2 multiplied by 2 is always 1. So, you can work out the symmetries of these direct products this way, alright. Okay. Direct product. So, for a direct product, one thing that we can take axiomatically, I thought I will prove it, but time is running out. So, instead of doing that, I would rather like to finish the discussion of IR activity and all. For direct product, say AB, which is equal to A cross B, chi AB for any symmetry operation R is given by chi A for that R multiplied by chi B of that R. That is what we just did, isn't it? Alright. What is the question that we asked? The question we asked is, does our direct product contain the totally symmetric representation? Okay. How will you answer that question? We answer that question by using our by now very familiar friendly neighborhood relationship. A1 is equal to 1 by H sum over R chi AB R multiplied by chi 1, it is a little difficult to write because it can be A1, A1G and so on and so forth. I will just write chi 1 R. Now, what is chi 1 R for every R for a totally symmetric representation? 1, right. So, this is just 1. So, you are left with 1 by H sum over R chi AB R, alright. Okay. And what is chi AB of R? Chi A R multiplied by chi B R. So, write it like this, 1 by H sum over R chi A R chi B R. And what is this sum? When is it equal to H? When is it equal to H? When A and B belong to the same symmetry species. No? Remember one of the consequences of great orthogonality theorem? Sum over R chi 1 R chi 2 R is equal to 0 if gamma 1 is not equal to gamma 2 and is equal to H if gamma 1 is equal to gamma 2. So, what we are saying is that these functions A and B must belong to the same symmetry species, same irreducible representation if this A1 is to be non-zero, right. So, is equal to H by H equal to 1 if and only if A and B belong to the same symmetry species, same irreducible representation, alright. So, we have now reached an important conclusion here. For a direct product, you are going to have the symmetry species occurring in the direct product if and only if the two functions belong to the same symmetry species, and then also A1 will occur only 1. is okay or not. So, this is something that we had worked out, remember. A j is equal to 1 by h sum over r chi r chi I chi j r. I do not remember whether I used I or j as a subscript, does not matter, right. So, now what I am saying is that what am I looking for? I am looking for the totally symmetric representation. So, for totally symmetric representation, this chi of r has to be 1 no matter what r is, is not it, and no matter what the character table is, no matter what symmetry point group it is. All characters are equal to plus 1 for the totally symmetric representation. So, this becomes 1. You are left with sum over r chi a b r, and here what you have written is chi a b r equal to chi a r into chi b r. So, substitute that, this is what you get, and then again we know that this is going to be equal to 0 unless A and B belong to the same symmetry species, and if they belong to the same symmetry species, then that sum is going to be equal to h by h equal to 1. So, this is an essential condition for a direct product to contain the totally symmetric representation, that the two functions must belong to the same symmetry species. Okay. But why are we saying so many things? We are saying so many things because we want to ascertain whether psi k v equal to 1 multiplied by x or y or z multiplied by psi k v equal to 0, this triple product, does it contain the totally symmetric species or not? Okay. It is very simple. First I take this direct product, then that with this, and life is made a little more simpler when you look at the forms of these wave functions. Okay, who remembers the v equal to 0 wave function for a simple harmonic oscillator? Yeah. I might as well show you. Here for some reason the quantum number is written n instead of v, but then what can you do? Can you read? I mean, that is not a general question. Can you read this page? So, see, this is what it is. N should be substituted by v actually. Okay. What is this h n? Hermite polynomial, and here we have some examples of Hermite polynomials in X. What is h0x? It is equal to 1. So, for v equal to 0 you substitute 1 here, what are you left with? You are left with ni, then e to the power minus alpha I by 2, then xi I square. What kind of a function is this? It is a Gaussian function, isn't it? It is a Gaussian function. So, it is totally symmetric, it is symmetric. A Gaussian function is totally symmetric, no matter whether xi is symmetric or antisymmetric. Okay, xi square is there. And what about h1? h1x equal to 2x, right. So, if you substitute 2x here, the initial part is symmetric anyway. Does it not mean that the wave function for v equal to 1 has the same symmetry as the normal mode of vibration itself? Because this will get multiplied by xi. Except for xi, everything is either a number or a symmetric quantity. Understand? What we are saying is that for 0th vibrational quantum number, for v equal to 0, the function is symmetric always. So, character is equal to 1, so it is totally symmetric. And for v equal to 1, what you have is, you have something multiplied by xi in the wave function. So, whatever is the symmetry of xi should also be the symmetry of the wave function for v equal to 1. right? Alright, are we okay with this? Now, so here the good thing is we can just write 1. Now we want to work with characters. So now I played Arjuna. I am only looking at the reflection of the fish. Okay, you agree? So what do I need to do now? I need to work with chi xi r. Okay, forget chi for now. So this I can replace by xi, right, the normal mode, and we know already how to determine the symmetry of normal mode. That is what we have been talking about for the last 2-3 days, right. Symmetry of x, y, z is provided in the character table, and in fact we now know character tables well enough so that even if it is not provided we can work it out, right. And then this thing is very nice, this turns out to be totally symmetric, right. So this is always 1. So your triple product now boils down to a direct product. It is not a triple product anymore when you talk about IR activity, isn't it, right. So I only need to worry about these two. And what is it that we learned a little while ago? We learned that a direct product would contain the totally symmetric representation if and only if the two functions which make up the direct product belong to the same irreducible representation. So now see what is the condition for IR activity. Now it is done. So condition for IR activity means the possibility of absorption of IR light, right, to excite a certain kind of normal mode of vibration. The essential condition boils down to be that the normal mode of vibration xi should belong to the same symmetry, same irreducible representation, same symmetry species as x or y or z. Now everything is hunky dory. You already know how to find the symmetries of the normal modes. You even know how to say to some extent what are the contributions of the to some extent which internal motions contribute to which normal mode. Now what you have learnt is that knowing the symmetry of the normal mode, you can say whether this normal mode is IR active or not, right. Any question? If there is a question, please ask. If there is no question, then we proceed with an example. So what is the condition for IR activity? Okay, what did we work out yesterday? Which molecule? AB3. AB3. We worked out two kinds of AB3 actually. First, what was the point group or the first AB3 we worked on? BF3 carbonate and so on and so forth. D3H. Molecule was AB3. What was the symmetry of the normal modes? You worked it out yesterday. Tell me. A1 dash plus 2E dash plus A2 double dash. Do we remember which is which? I remember A2 double dash because A2 double dash is our very favorite out of plane doming motion. What about A1 dash? It is symmetric stretch and no bend, only symmetric stretch, isn't it? Only symmetric stretch, because here only we learned that even if you use the angles you get A1 dash, but that is a redundant coordinate, you have to throw it away. Okay. So, A1 dash is pure symmetric stretch. And what about these 2 E dashed? How many normal modes are there in the 2 E dashed? 4 normal modes. What are they? Yes. So, there are mixture. Okay. What is the percentage of mixture? We cannot really tell unless we go a little further, which we will not. So, we should be happy with that. Now, I want to know which of these are IR active, which of these are IR inactive. Alright, D3H. D3H. What are the vibrations? Cannot see anymore. A1 dashed, E dashed, A2 double dash. Okay. Do I what are the symmetry species of X, Y and Z? Can you read? Oh, yeah, very nicely. Z is A2 double dash. Huh? What about X and Y? E dash. Right? Remember that. So, this should be IR active, these should also be IR active. Moreover, do not forget something, that this A2 double dash gives you a totally symmetric representation in the triple product only with Z, not with X or Y, right. So, what it is going to do is that it is only going to absorb the Z component of the light. So, this is called Z polarized transition. Z polarized transition. And what about E dashed? It is going to absorb the X component of polarization, Y component of polarization, and we all know what polarization is, right, linear polarization. What is polarization? You can say oscillation, right. So, the plane of oscillation is only one, that is plane polarized light. When you mix X and Y, then you get circularly polarized light or elliptically polarized light depending on the coefficients. Okay. So, this is a Z polarized transition, this is like XY polarized transition, alright. So, using polarization resolved IR spectroscopy, you can actually identify the bands a little better, you can say which is which a little better. And what about A1 dashed? A1 dash does not show up in IR spectrum. Huh? So, poor A1 dashed, is there no way of seeing it? Actually there is, you see it in Raman. Okay. How do you see it in Raman spectroscopy? Let us see. I will keep this aside, we will come back to it a little later.